My name is Jan Krause. I'm working at Fraunhofer HHI, and I want to talk about dynamic rerouting of quantum key distribution systems during live operation. So what do we mean by this? We'll look into this in the next slide. So basically, the scope of the talk is about how can we increase the robustness of QKD systems in actual deployed networks and also for free space optical links, and how can we make them more robust and resilient against disturbances of the quantum channel in different kinds. So let me start by giving an introduction. We will have a look at the resynchronization method that we introduce, some experiments, and then finally some discussion. If we have some time left, or if some of you are interested, one of the reviewers, for example, mentioned he would be interested in looking into the security implications and potential new side channels. We can also have a look at that. So first, we're talking here about prepare and measure QKD systems. The synchronization method might also be applicable to other protocols and systems, but that's what we are looking at. And we specifically have a 1 decoy time in phase BB84 QKD system operating at 625 megahertz qubit transition rate, just that you have some understanding of what we're dealing with here. So typically what you need for a QKD system is a couple of channels that connect Alice and Bob. So of course you need a quantum channel in order to transmit qubits, but you also need a classical channel for post-processing, but also for monitoring and control of the system. So Alice and Bob just have to talk to each other, for example, in the initialization routine, even before you start transmitting qubits. And then, at least historically, systems have also used what I call syntonization channel. So we should clearly distinguish between the two things, syntonization and synchronization. What we mean by syntonization is basically that we ensure that Alice and Bob's clocks are running at the exact same frequency with phase stability. And then with synchronization, we mean that the remaining offset between the two clocks are actually the same. Why do we need this? For every single photon detection that Bob has, he needs to be absolutely sure which qubit index, and even in our case we have 2 time bits per qubit, which time bin to assign this detection to it. There's an error in that, of course the qubit will be 50% and no key can be created. So, however, network operators, for example, they want to reduce the amount of channels that are required and that you need to actually deploy a QKD system, because every fiber and every wavelength channel even that you use in a network will of course have a price and a cost, and you want to reduce the requirements as much as possible. Furthermore, we want to allow for the quantum channel and the classical channel, basically all the needed channels, to be routed via different paths. So what our system, for example, has already supported for quite a while is that the classical channel can be routed. It doesn't even have to be optical, it can be via whatever, and it can also have very high latencies, up to, for example, even a second, which of course means you need to do the synchronization then via the quantum channel. And we will look into how we're doing that on one of the next slides. But what about the synchronization channel? We actually also want to get rid of that. And there have been a couple of publications already where this has been done. Then, of course, you save some resources in terms of this fiber connection, but also then, of course, you need kind of stable clocks at both sides. What we are using in our implementation, it's low-cost quartz oscillators. So these are no special clocks in any kind, no rubidium clocks or whatsoever. It's really like a $10 clock that we're using. However, now we need to do the syntonization, so the clock frequency recovery based on the single photon detections. So we're doing this via the, basically via the quantum channel and the detections coming from that. Now, what happens if there are disturbances to the quantum channel? The syntonization and the synchronization will get lost. You can always quickly regain the syntonization, because as soon as you have detections, you can statistically analyze the detections and, for example, via a histogramming method, regain the syntonization, but the synchronization will still be lost. So now the question is, how can we increase the resilience of the quantum channel, or how can we reduce the requirements towards the quantum channel such that it allows for a lot of dynamic systems and application scenarios. Before we look into how we solve this issue, let's first look into what is actually the problem or what can cause the problem. At least there are 3 factors that can lead to synchronization loss, and typically for at least most systems that I know, this led to a need for restarting the system. For example, if the synchronization is lost and you're not somehow actively regaining that synchronization, you have a keyword of 50%, and you have to restart the system, and that of course takes some time. It can be up to a couple of minutes. So synchronization, for example, it can be lost due to statistical fluctuation in the single photon-based synchronization step that I mentioned, since we're not using the synchronization channel anymore. But then there can also be quantum channel interruptions, and there can be multiple reasons for that. So for example, in fiber-based networks, some technician might just detach a fiber and reattach it, but if your clock synchronization doesn't work in that meantime, you basically have an offset coming from that, and your qubit is 50%. But it could also be that in a actual fiber network, like the software-defined networks, where more and more adaptability and dynamic routing is now coming into the networks, network operators might want to reroute optical channel connections while systems are operating, in order, for example, to fulfill some new throughput demands on in the network. For free space channels, you can have things like cloud coverage, basically blocking your link. There can be a bird passing the line of sight, and also if the tracking has some issues and doesn't couple the light properly into the single mode fiber for a certain amount of time, you would also lose synchronization. And then also for both fiber and free space networks, if you do such a rerouting in a software-defined network, the 2 paths that you're using, they can be quite different. And for free space networks with mobile nodes, when a satellite is moving or your drone, as we saw earlier, is moving during the time of that channel interruption, of course, you also have an additional offset to recover. So all this leads to system restarts being needed. And our idea for how to approach this problem is to transmit short fixed pulse patterns over the quantum channel in a periodic manner. And I said that initially our system has to obtain the synchronization. So for this, we transmit a synchronization pattern. So if you want to look at it, this is actually the method that we use here, which achieves even sublinear complexity for the offset recovery, allowing with just a couple of thousand operations on a modern CPU to recover offsets up to seconds even. Then we transmit qubit blocks, so this can be in the order of a second, for example, or 10 seconds, and we interleave into these qubit blocks resynchronization blocks, for example, of the duration of 20 milliseconds, which is a fixed pulse pattern, and it's always the same. It's known to Alice, Bob, and of course also Eve, if you want so. So what does Bob now do? So Bob needs to, in case there is an additional offset, he wants to find this offset, we call it delta, and basically you can do this by calculating a cross correlation. However, if you look at the time scales that we have here, it means that you would have to calculate a cross correlation for a pattern that's roughly 10 to the 7 symbols long, and if you calculate an FFT of such a big vector, it actually takes a considerable amount of time and needs a lot of resources. And since we're doing it here repetitively, you do not want to do this all the time. So our idea is actually to not use an FFT or any complicated method for calculating the cross correlation, but to really go down to the basics. First, of course, you need to align the detections again to the time bins, because there might even be a sub-time and precision shift of the detections. Then we convert to time and precision, and with this vector we work then. And we start by testing an offset of delta equal to 0, which means in the most likely case, when the system is operating normally, we check for the correct offset, and we basically the algorithm directly terminates. And if this is not the case, you can see here to the right, we basically increase this delta in this pattern of testing first 0, +1, -1, +2, -2, such that the most likely offsets, which should be close by in most scenarios, are covered quite quickly. And so for this, you do not need floating point operations and no FFT, and this evaluates actually pretty quickly. So let's look into how we tested this experimentally. We wanted to basically simulate or create a very challenging scenario that resembles a real fiber-based network with rerouting capabilities. So the quantum channel we replaced by this thing here. It's an optical switch that allows for the routing through different fibers with different length, and it also allows for interrupting the fiber channel. And we used a deployed fiber of almost 14 kilometers in the Berlin quantum test bed, and an additional 2 fibers of 25 and 41 kilometers, plus an always 25 kilometers in the link. So how did this perform experimentally? Yeah, the system recovered pretty quickly from multi-minute channel interruptions and fiber length changes even up to more than 100 kilometers. You cannot see it here in the plots, but we've just checked it by plugging fibers into fiber spools, and it really works nicely. So what you see on the top is the recovered clock drift. So basically from the synchronization step, the drift that was recovered based on the single photon-based synchronization. You see it's actually, even though we have low-cost quartz oscillators, it's rather stable. On the second, in plot B, you see the accumulated recovered offset. So in the beginning, on the left side, we started by applying the 4 different fiber lengths for 20 minutes each, just to basically check if everything is working as intended. And then we applied another 70 quantum channel length changes up to 40 kilometers with a time difference of 2 minutes mostly. So this is already quite challenging because in most network scenarios you would not really do this. We see then they recovered the time needed for the offset recovery. It's 50 microseconds in the typical case where there's no additional offset, and then around 7 milliseconds for each additional kilometer that you have to recover. You see the detection rates, and there we had a 2-minute channel interruption. There were basically only noise detections, and then within really very short time, the offset was also recovered in that case. And we did not have to restart the system over this period of 7 hours once, and even you see the secure key rate, so even for most of the blocks there was, except of a couple of exceptions, key generated, and the secure key rate were mostly just impacted by the different fiber length and resulting channel attenuations. So summarizing or discussing, our method provides a lot of additional flexibility for software-defined networks, so you can reroute over very long length differences and with different paths, or maybe this might also be interesting to cover fiber damages. For free space links, this enhances your flexibility when there are tracking issues, cloud coverage, or birds passing by. Basically, the method has no drawbacks. You're only reducing the time that you're transmitting qubits by a very small fraction. And in the standard case where there's no additional offset, it evaluates very quickly. It's implementable on lower level hardware because there are no floating point operations needed, no FFTs. You could implement it on an FPGA, for example. And it can be easily retrofitted to existing systems because the subsystems of the QKD systems do not need any additional inter-subsystem dependence. There's no information that you have to pass between them, so you can basically, in the post-processing, add that as an additional step in the post-processing. Okay, with this, I want to thank you for attending the talk, and of course my teammates who all contributed to building the system and making this happen. Yeah, thank you very much.
It's a very nice talk. And any questions? So I have a question. So it's a very nice idea that you can adjusting the time synchronization during the path length is constantly changing. So my question is that in practice, either for satellite-based or drone-based quantum communication, the length is changing continuously, but you are routing by the optical switch, so that basically you are the path length jump by steps. So do you have any idea of how your system really work when in practice systems, and how fast is the length changing speed? Can your synchronization method follow?
Okay.
Thank you.
Yeah, thank you for the question. So I think it's basically two different problems that are tackled by two different steps in the synchronization and synchronization. So if there's a continuous change of the length difference, like when a satellite is flying over, this would be covered by the synchronization step. So if we look at this plot here, basically the upper curve in subplot A, it would not be constant, but this would have maybe some kind of a dip. And the resynchronization method in this case would not even have to do anything. But let's say there is some tracking issue, and while the satellite is moving and also maybe changing its velocity, the channel is blocked, then even if you regain the synchronization, there will be an additional offset due to this movement, and this then you can recover by the resynchronization. Of course, we haven't tested this with a satellite link, but this has been used on free space links already with a static free space links, where we had a lot of turbulences over 1.7 kilometers, for example, coupling into single mode fiber, and there we observed a lot of interruptions due to, for example, turbulences, but we also just tried covering the telescope by our hand, and it would just recover synchronization properly.
Okay, thank you.
Thank you for the talk again. So with this synchronization and synchronization technique, you say you have this 20 millisecond burst in the quantum channel. Is that then like a bright source of light that you have to send through? And if that's the case, how do you sort of filter it out to make sure it doesn't interfere with the single photon detectors?
Okay, yeah, thank you for the question. So as I showed here, actually we're always sending pulses on the same mean photon level as needed for the qubit transmission. So that's around 0.17 and 0.47 photons per qubit, I think. And with taking into account the 650 megahertz, that's around minus 75 dBm that's being transmitted. But of course, it also works when adding additional attenuations from the channel. But these 20 milliseconds that I mentioned, of course, you have to select these properly in order to lead to a sufficient statistic for this cross correlation to actually work with a high enough probability. Maybe, I don't know if we have enough time to look into this, but I analytically also looked into how should you choose these parameters. So for example, if you want to have a given success probability for one resynchronization to lead to the correct offset, and you want that the resynchronization does not fail with 1 minus 10 to the minus 6, for example, per day, if you do it once per second, then you can find that, for example, parameters like choosing this offset acceptance threshold for the cross correlation at 0.5, this cross for the experiment, and a number of detections that you process for the block as something like 500. And then based on this and all the parameters that are given from your QKD system, you can choose how long should these resynchronization blocks actually be.
All right, thank you.
Okay, so due to the time limitation, let's thank the speaker again.